Hello, everyone, and welcome to today's Department of Energy Innovator Fellows informational webinar on electric system reliability. Thanks so much for joining us today. We have a wonderful presentation here for you, and let me introduce our presenter. My name is Miles Collins. I'm a policy researcher at Berkeley Lab. I am just going to give a brief welcome and introduction, and then I will pass it on to JP Carvallo. Just to give some information on JP, he's a research scientist in the Energy Markets and Policy Department here at Berkeley Lab. His research focuses on long-term power system planning, integration, and planning of distributed energy resources and reliability and resilience valuation. JP holds PhD and MS degrees in energy and resources from the University of California, Berkeley, as well as PE and Bachelor of Science degrees in electronics engineering from Universidad Técnica Federico Santa Maria, Chile. As we go through this informational webinar here, you can enter questions in the chat box at any time. You could also raise your hand and ask a question live, and then JP will call on you to unmute yourself and ask your question. Just want to put a quick plug for some upcoming future informational webinars. We have two coming up later in the summer. We have one on July 24th on program planning and evaluation. So Steve Schiller is going to be giving a good chunk of that one, along with a presentation from myself as well. And then following that one is August 7th on data centers. So the registration links are here in the slides. The webinar started at 2 p.m. Eastern. If those are open for registration now. And without further ado, I'm going to pass the microphone here to JP. And JP, I will also pass the sharing privileges here. So go right ahead when you're ready. Thanks.
All right, you're welcome. Thanks, Miles and everyone, for the invitation and to present today. Happy to be here sharing some knowledge on electric system reliability. So as Miles indicated, let me see, I'm not, as I'm sharing and doing the presentation, I don't know if I have, yeah, I think I have the chat here. So if you folks have a question, drop it in the chat. I may take maybe a slide or two. So if you will, my slides should be numbered. Let me just quickly say, yeah, you see numbers in the bottom right. So if you can put slide 2, slide 4, and then you put your question, I will know if I went past where to go to look for. So today we're going to talk about reliability in power systems. And in doing that, we're going to cover, we're going to start from high up in looking at what has typically been, three pillars in power systems planning and operation. Reliability being one of them. The other one is affordability, is how we operate the system to at the lowest possible cost. And the other one is, environmental impacts. It is one of the classic, one of the several impacts that power systems can have, but it's been tracked for some time. And these three are usually in some sort of tension. Higher reliability costs more money, and making the system more affordable might, reduce reliability. And so there is indeed a fair amount of relationship between technical and economic aspects of reliability that we will cover today. Reliability is a property of the power system that, in general, informs how often power will be available to customers. More reliable systems are guarantee that availability of electricity to end users is higher. And now power can, of course, be unavailable for multiple reasons. In this description here of reliability, you can see there are 5 different groups of components of reliability that are really focused on a mix of the location in the power system where things can go wrong, and in some aspects of the process of power systems, meaning if it's an investment versus an operation of the power system. You can see that in this particular chart from the energy system integration group, ESIG, resilience shows up as a subset of reliability. We'll briefly refer to relationship between reliability and resilience, even though this presentation is 99.9% focused on reliability, but just so you folks know how they might relate to each other. Um, as I mentioned, reliability in power systems is assessed differently across the grid and is intentionally focused on specific components of the system. In general, reliability is studied, tracked, and assessed at the generation, at the transmission, and at the distribution levels independently, where the generation and transmission tend to be connected under the bulk power system assessments. But there is a distinct relationship or distinct treatment of reliability between the bulk power system and the distribution system. One of the key reasons why we do this is because of the impact that unreliability has when it happens at the bulk power system level, given that the bulk power system has a much wider impact in when there's failures compared to more localized distribution system level issues. You can think of this as in our bodies, the brain is kind of a centralized of all the electric signals and nerves, and the rest of our limbs and body are sort of radial extensions of that. But ultimately, anything that's happening in a finger in terms of nerves and sensation goes back to the brain, is processed, and goes back then to the finger for some action. Like if I'm burning, I have to get my finger out. All this does is process up. So that's why we have a strong skull, giving our brain high reliability and resilience, whereas we have just soft tissue in most of our body. So the power system reliability approach is kind of the same. We focus extensively in the bulk power system to prevent interruptions and outages of different sorts. And then we do track and also prevent interruptions in the distribution system with slightly different focus. As I anticipated, there is a relationship and there are technical and economic aspects of reliability. On the technical side, we're focused on establishing metrics to know how reliable a system might be. We're focused on extracting data and producing data to inform metrics and track performance. And then there is a focus on methods to assess reliability. As you might imagine, the power system is a kind of system where we can't run experiments. We have to create models on a computer and then run experiments in those models. We can't really do anything on the grid itself. It will be too disruptive. So just translating the grid into those models and then using different methods to run those models and get results from them requires a number of methods, a number of approaches that we will cover in this presentation. At the same time, from an economic perspective, as I mentioned, there is a cost in achieving a certain reliability. And so how much and what is the least cost way to create a system that achieves a certain target is a key question that utilities and system operators grapple with. Conversely, there is a question about how much are customers willing to pay for certain layers of reliability. So in one side, we have the cost of building a reliable system. On the other, we have what are the benefits that customers derive of having a system that's reliable to a certain extent. This carries an interesting possible angle, which is whether reliability could be tailored to customer needs. And we're not going to talk about this extensively, but there are indeed many examples, especially with industrial customers, where they can receive improved or worse reliability with an economic trade-off. And then there are, of course, from the economic perspective, market and regulatory design needs to incentivize investments that allow the systems to be reliable. As we will explore, the system is reliable in part because we operate it in a way that makes it reliable, but also because it has enough assets and the right type of assets in the right places to ensure that the system operates with certain performance levels. So we'll cover specifically the investment side is tricky because, of course, many of our systems investments are lumpy and long-lived. So we're going to cover some of the specific incentives that are designed for that. And just to wrap up this sort of economic and technical element of reliability, I wanted to show this very clear chart developed by ERCOT, the Reliability Council in Texas, where they analyzed, and a lot of this graphic won't make sense right now. Hopefully, it will be easier to digest towards the end if you know nothing about reliability right now. But this graphic is showing essentially all the way to the left, the system is underbuilt. It has a very, very small amount of slack. And so the total system costs are relatively low in the if you can see in the bottom pink line. But the costs of not having power, which are the green and red lines, all the way up, grow significantly. The system is just spending a whole lot of money compensating customers for power they didn't have. All the way to the right, we have a system that has very little, it's very, very reliable. It has very little value of lost load, very little cost of power not served. But the system is much more expensive. It is more costly to build that system. So you can see that ERCOT in his analysis found that right there in the middle is where they had what's called a reserve margin. We'll cover what that is later on. And that was the sweet spot in which they built a system to a level that accounting for the costs of not serving certain amount of power and expectation, that was the minimum in across all these possible scenarios in terms of all the way to the left, a very unreliable system, and all the way to the right, overbuilt, super reliable system. And so this suggests why we can have perfectly reliable power system is that if you keep going to the right and you keep minimizing and minimizing the cost of energy not served, the system cost will keep increasing exponentially. And as I mentioned, I didn't want to get out of this intro section without mentioning very briefly the relationship between reliability and resilience. They are, of course, related concepts. In some cases, they're framed as in that first ESIC graphic that I showed at the beginning, where they're hierarchical, derivative, such that they depend to each other. In that particular case, they were shown as resilience being a subset of reliability. In this particular case, to the down right, this figure from the Organization of MISO States, OMS, they show like a spectrum. I go from reliability to the left and then move into resilience to the right, depending on the types of events that I'm subjecting the grid to. In some of the cases, some researchers have really tried to frame reliability and resilience as distinct. It's very different things. I have been following personally, and I think the industry is following towards creating reliability and resilience as two complementary topics, complementary concepts. For example, DOE's Modern Distribution Grid report describes reliability as an objective of the grid, where resilience is an attribute of the grid, in such a way that if you enhance resilience, if this attribute of the grid is enhanced, I can more easily achieve the objective of producing and delivering power consistently to end users. And so yes, so we are all on the same page. And just in case, the resilience definition that is underlying here is the one that's coming from one of our recent Grid Modernization Lab Consortium, GMLC, which is the ability to prepare and adapt to changing conditions and withstand and recover rapidly from disruptions. And so this is both encompassing deliberate attacks or naturally occurring threats or incidents, extreme weather events, etc. So this idea, this notion of preparing, adapting, withstanding, and recovering is typically associated with resilience across infrastructure in general, not only power systems. And so as the infrastructure is behaving in this resilient way, then the reliability as an operation and objective with the power system is also achieved. All right, so following this distinction between technical and economical, and the distinction between the different domains in the power system, I'm going to split this presentation in three big groups. We're going to spend a fair amount of time talking about the technical perspectives of the bulk power system. Then we're going to spend a little bit less time, largely because there's not a whole lot of work in that space, but we're going to spend less time talking about the technical perspective on the distribution system. And then finally, we're going to spend a few slides discussing some economic elements. So as I mentioned, we're going to start with the bulk power system. This encompasses generation or any power plants, now storage also, transformers that step up the power to the high voltage transmission lines, those really big lines that you see out. This one, it says 400 kV. They can go up to 750 kV easily, and they can even be DC tie lines, direct current instead of AC tie lines, and those can be up to 1,000 kilovolts. And then we stop at this substation before we go into the medium voltage, which is the 13 kilovolt, the typical. There are multiple voltages at the distribution level, but that's a typical one. So this is where we're going to be focused on over the next few slides. So when we focus in this particular bulk power system space, we start seeing specific definitions and specific authorities or organizations that look at this. So one of the main important ones that you want to track is the North American Electric Reliability Corporation, NERC. And NERC has a much more refined definition of reliability for the bulk power system. In their minds, is operating the elements of the bulk power system within equipment and electric system thermal, voltage, and stability limits, such that instability, uncontrolled separation, or cascading failures will not occur as a result of any disturbance. And they explain what kinds of disturbances they're including. This definition includes some interesting elements that we're going to be talking about later on, but thermal violations happen when you're trying to push too much current through any type of equipment. So that means that you are underinvested. Voltage can happen because of that, but also because of dynamics. And stability aspects are entirely operational, or for the most part, operational. So you can see and that this is covering aspects related to investment, aspects related to operation, and some aspects related to emergency, things that can go wrong. So from that perspective, we're going to split our discussion of the technical aspects of bulk power system reliability in three buckets. We're going to talk about adequacy, which you might remember. Just some of these are copying what was in that first easy graphic that I showed at the very beginning. Adequacy is the study of whether there is enough capacity to meet load at every single hour. And the focus of adequacy is in long-term planning. So we're talking about a time frame of years or months. We're going to also talk about operation on bulk power systems and how operational reliability and stability studies are focused on short-term issues like balancing, voltage and frequency response, and the use of reserves. So in this case, we're talking about keeping the system operating in the very short term. The need for focusing on operational reliability is largely because the bulk power system and in general the power system operates in a just-in-time fashion. There is no way we can just tell a load, hold on, we're going to meet your need in about a couple minutes. That's a blackout. There's no way to store, up until recently, no way to store power effectively to serve load in different times. We're now having a little bit more storage in the grid, but it's certainly not enough to be similar to what you can do with water, for example, or tomatoes out of the farm, where you can, store them in warehouses and then deliver them as they're required, as demand increases. In this case, we have to meet demands in instantly at the same in real time, and that requires a fair amount of fine tuning of the system to keep this machine rolling that we're going to study here as operational reliability. And finally, there's a third bucket here that I call contingency aspects of reliability, which is mostly preparing for things that can go really wrong. So operation is preventing that the system doesn't go, that nothing wrong happens. Contingency is when something happens, what do we do? So in this case, the focus is on avoiding catastrophic blackouts and the types of emergency response. What we're going to discuss here is going to be largely how entities can create backup or can create contingency response plans, and some specific technical elements related to how to avoid or recover from blackouts. And as you can see, the timeframes involved here are in the minutes to seconds with its contingency, when we're trying to really avoid a large blackout. And then it can go into the days or hours when we're talking about recovery. Recovering the power system is a non-trivial task. There's goes a lot that goes in there, and I consider that part of the reliability of the power system to at least recover. Some people might say that recovery falls more on resilience. That's where these, definitions get blurred. So let's start with the adequacy. What is resource adequacy? You may have heard this term. It's been a hot topic lately for a number of reasons. In part because there's this, over the last few maybe decade, we've had some pressure to start retiring plants that are uneconomical. And then there has been a fair amount of types of resources going into the system that are not dispatchable and that make it a little trickier to understand whether we're going to have power at the right hours when the system really needs it. And so we have to, the ISOs, the independent system operators and utilities in the US have had to do a fair amount of work to catch up with these new developments, which is also happening across the world in other countries as well. So resource adequacy is going to be defined as the ability of the electric system to supply the aggregate electrical demand and energy requirements of the end-use customers at all time. And this is taking into account potential scheduled and expected unscheduled outages. So essentially, this is a NERC definition. I put an REC, but this is NERC from 2025. Is their latest glossary definition, but it was adopted 20 years ago. And so you can see that NERC in a different document 10 years later define adequacy in a more succinct way, but we define it in an interesting new addition where it says is the ability of the electric power system to meet demands for electricity using supply and demand side resources. So in the definition from 2011 that was in a different report, NERC is alluding at the fact that we can use both supply and demand side resources to meet demands, and not only what you infer from the first definition that's 20 years old, which is on the supply side. This shows a little bit of some of the evolution in the thinking of what adequacy is and then how we assess it. A couple of years ago, we drafted a report that we called a guide for resource adequacy assessments in the sort of in evolving power systems, and we came up with these components for resource adequacy framework. What I was just discussing is this definition of resource adequacy, which again has not been trivial. It has been changing a little bit over time. When do we establish that a system is adequate? When do we know that the system have enough investment, enough capacity to serve load within a prescribed level of reliability? With that, there are specific targets and tracking metrics that you have to define that have also been evolving. There are methods, models, and data that have also been evolving quite substantially over the last decade. And then all these three pieces of resource adequacy assessments have to feed into a resource procurement decision. Like if I'm assessing whether my system is reliable or not, and I find out that it's not reliable, then I need to procure resources to ensure that I can meet certain reliability levels. And that changes depending on what my jurisdictional setting is. We're going to talk a little bit about this later on. And then we have been proposing, and this is not quite available yet, that as you can imagine, a lot of what happens here in the blue blocks are modeling. Is all modeling, all sort of theoretical, if you will. So we have been proposing that the result of these models should be somehow anchored to reality. One key problem is that we don't, fortunately, have a whole lot of events, reliability events happening in the bulk power system very often. You might not even remember the last time you had a blackout because of a power system. You may have had an outage, an interruption in your own house, but it's very likely that that was a distribution system issue. I can count in one hand the large-scale interruptions that have occurred over the last decade or two that were because of bulk power system issues. But there are still ways in which we can conduct respective evaluations to ensure that the results of our resource adequacy assessments are anchored in reality. So I described these different components. I was gonna elaborate more on them, but I think we have enough, and I think you folks understand that there are, at least 4 key pieces here, and we're gonna be discussing these as we move forward. In addition to the pieces that go into resource adequacy assessments, I wanted to pass at the onset, what are the components of a resource adequacy process? And even though these processes for resource adequacy are done both by independent system operators like MISO or PJM, and by utilities that are conducting and are balancing area authorities and conduct their own IRPs, mostly in the Western US, I chose to use a process that, in this particular case, MISO conducts, because it's a kind of very typical structure of how you conduct resource adequacy assessments and connect them to market-oriented decisions. So you can see here that there is at the left of this diagram, there's a probabilistic risk model that is in charge of assessing through a number of inputs, assessing what are the likelihood of the system not meeting certain reliability targets or having shortfalls. In this case, the MISO uses this probabilistic risk model to identify seasonal needs and to produce a number of metrics that describe how the system is performing under the current investment levels and the types of events that could occur in the system. And these fold into 2 key processes that we're going to discuss later: accreditation and the planning reserve margin calculation. And in turn, these inform the blue blocks here, which are all the planning and procurement needs that have to occur within MISO. So I just wanted to make sure that we differentiate the resource adequacy assessment portion, which is here to the left in the analysis, which is how do we know that the system is reliable or not? And then what happens to the right, which is the output of this feeding into subsequent elements of a process that tries to ensure that we can meet reliability targets that we have set by investing in the right places and the right types of technologies. Um, I have a comment here. Oh, it seems that it's yeah. So someone was talking about Puerto Rico and sort of joking about the ability of the Puerto Rico grid operator to test the black start process. That's yeah, it's an unfortunate true thing where Puerto Rico has been suffering from way more unreliability at the bulk power system level that it should, and so that has enabled indirectly the system operator to practice black start, which is one of the services to bring up the system from a blackout, which is non-trivial, and we're going to cover that in the contingency bucket later on. In terms of assessing resource adequacy, the methods largely over the last, I would say since the 1970s up until the 2000s, 2010s, what we used to do was a much more deterministic analysis that was largely looking at historical performance of the system. It was heavily based on just historical performance of plants, how often they would go on outage, what kind of weather was affecting them, etc. And it tended to look just at the peak hour or maybe a few top load hours. And it was just making sure that the system had enough of a buffer within those top load hours to say, okay, I think we're gonna be okay. In general, systems in the past were not unreliable because of this approach. What I tend to see, what we tend to see over time is that the systems were overbuilt. Large portions of the bulk power system were overbuilt over time for different reasons. In part because in the 70s there was a huge increase in load that led to a lot of build out of the bulk power system. Then later, as it tapered, produced slack that the U.S. power system enjoyed throughout the 80s and 90s. And then when the ISO world started existing in the late 1990s, they inherited this more spacious power systems that had been already paid for the most part because they had been paid for through regulatory approaches. Now, in the modern approach, we are in a world where we consume a lot of that slack and we really need to invest. We have another wave of load growth coming through. So we have now probabilistic analysis that are really trying to get at examining a lot of random events that could happen and how my system can react to these random events, such that we can really get at the detail of how the system performs under most possible events. We do these by simulating the system across a wide range of conditions, and we look at all hours of the years. So things have been moving from this legacy approach, and I'm going to be, of course, talking about this modern approach over the next few slides. So right now we're going to go a little deeper into how we conduct this probabilistic resource adequacy assessment, and I'm created this figure that I think does a decent job at explaining what we're looking for when running these probabilistic assessment models. So you can see here that we have probability distributions. These are in blue, the probability distribution of generation levels. So for every given hour in the system, I'm simulating how much power I have available. There are many ways to do that more or less accurately, but at the very least, I'm trying to capture the fact that certain types of resources like solar and wind have a certain availability of resources. In particular, solar, I know that I don't have power at night or in certain times of day. And depending on the location, I know that wind might have certain probability of having certain levels of power. And so in addition, I also have thermal resources that might be in outage for different reasons, or that might have been operating less efficiently because especially operating thermal plants in summer seasons degrades their power substantially. And so there are all these weather, economic performance, other variables that are influencing the generation side of things. Why I don't have my full nominal capacity at every single time. You can see here in the chart that the very right-hand side of this blue curve sits at maybe 7,200. That will be your nameplate capacity, the maximum you can get. But for all these random reasons, the median value that you get is closer to 6,500. That's really what the system on average can give you. In red and green, I have load in red and load with energy efficiency in green. This is just showing, this was taken from prior work where I was sort of trying to explain how energy efficiency can actually contribute to resource adequacy. And you're going to get sort of the little extra um, benefit there here from that. But focus on the red curve. Load also has a maximum load, a peak load that shows up just in specific times of the year. But in general, the average load will be, in this case, closer to 5,000, much lower than the median generation level. But as you can see, there is a point where the red curve goes over the point where the blue curve is. You can see that there is that gap down there, and that's the probability that in a certain times of the year in my simulations, I might have load that is exceeding generation. That is the loss of load probability that we're trying to track in resource adequacy assessments. Now, these types of results come from simulating thousands and thousands of hours. Usually you run entire years and you run them thousands of times. We're talking about potentially 500,000 of runs where I throw the dice to get a certain level of generation and I throw the dice to get a certain level of load. And this is showing that there's a certain level, there's a certain amount of hours where I might have more load than generation, which means that I could have a shortfall. And this is what this particular approach is measuring, the number of shortfalls. In particular here, just in the green, as energy efficiency pushes load to the left, so I have load on average lower because I have energy efficiency. You can see that it contributes by reducing the area under the point where the blue and red curve meets. And in this case, the area under the green and blue curve is very, very, very small. So you can say that the probability of the system having a shortage when I add this efficiency is much, much lower. In terms of metrics and targets, we're going to talk about frequency and then some duration and magnitude targets. This is, if you have been following resource adequacy, you have heard about it, you may have heard about this criterion, the 1 in 10 criterion, which means 1 day every 10 years. And this is called the loss of load expectation, or LOLE. This metric measures the number of days in which in these simulations, I could have at least one shortfall in that day. This is kind of interesting in what it exactly means. This is often interpreted as, oh, I'm going to have 24 hours of interruptions or outages over 10 years. Or then I'm going to divide this and say, oh, this is 0.1 days per year. Now, 24 hours of interruptions in 10 years, at least one shortfall per day every 10 years, and 0.1 days per year, all three of them are different things. They have been used equivalently over time, but there is clear research that shows that these are different things from a statistical perspective. And they can produce systems that actually achieve different performance objectives. Now, going back to what's happening is that the system planner is really aiming to have enough capacity in the system such that the simulated shortfalls, like the ones that you see here, the points, the number of times where the blue is under the red is only 1 day every, 3,650 days simulated in my model. So that gives you a sense of, and then if you can simulate this or try to translate this into hours, then some people say, well, we're going to try to have at most 2.4 hours, that's 0.1 day, 2.4 hours of outage in year on average in my simulation. An alternative metric is the loss of load probability. And this is the probability of having at least one shortfall during a period. And that shortfall can be of any size. A shortfall, as we understand it here, is just the amount, is the specific instance where I have more load than generation. And in this case, you can see here that there is this area under the curve again. And in this case, I might use the fancy, because I've been referring to this area. So just in case you missed it, this area here under the red curve and to the right of the blue curve, this is the number of instances where there was a shortfall. We can maybe think that there were, out of the 500,000 simulations, maybe we had 5,000 of instances where we had a shortfall happening. So that means that we have something close to 0.1%, a 1% loss of load probability. Typically, the values that are used for loss of load probability are, let me clear here, are closer to are typically in the 3 to 5%. There is an equivalence that exists between these loss of load probability and this 1 in 10 loss of load expectation that we have been using historically to plan our systems. But there are especially entities in the West that are using this loss of load probability. Now, the LOLE and the LOLP measure a probability or an expectation of something happening, but it doesn't tell us anything about how much energy we're not going to serve or how big the shortfall might be. And as you can think, it's different than if I have a small shortfall that just misses, just a little bit of load versus if I have a massive shortfall that doesn't serve an entire state. And so that's why more recently, planners that run these resource adequacy assessments have been including different additional types of metrics. In this case, the expected unserved energy measures the magnitude of the shortfalls, how big these are, and this is usually expressed in parts per million. And then there are two metrics that try to measure frequency: the loss of load events, that tries to measure the number of events that have at least 1 hour shortfall, and the loss of load hours, which is a duration metric that tries to count the number of total hours that are simulated where a shortfall occurred, regardless of the magnitude. So you can think that these different metrics give you pieces of the puzzle. And this is an example of how that works. For example, in this chart, you can see here there are in the left two types of events, A and B. They are both have 4 hours of shortfall. So their loss of load hours is 4, but the event above produces a much higher energy not served because the shortfalls were much bigger. And so with some metrics like loss of load hours, you would both say the systems are equivalent. But if you use the energy unserved, you will quickly say that the system above, the system A, is substantially larger or less reliable than system B because it has a much larger shortfall value, a much larger magnitude of the events. Similarly, to the right between C and D, you can see that both have 3 instances. So the loss of load events are 3 on both, but the loss of load hours are 3 on both. In between C and D, there are 3 specific hours that didn't have power above and 3 specific hours that didn't have power below. But above, this is mapped in such a way that you can see there are 3 distinct events that are occurring. And so the loss of load events is 3, whereas the loss of load event in D is just 1. It's 1 long event. So this hopefully reflects why it's important to use these multiple metrics to track and then establish objectives for our system. And so hopefully you all understand why the 1 in 10 metric that still remains very prevalent. You can see here in this collection or survey of resource adequacy metrics that most of the US still was using the 0.1 days per year as a criterion. This is a little bit dated, it's about 5 years ago, but this remains more or less true. There are very recent efforts by MISO and PJM, at least, maybe some of the other ISOs as well, to add, I think ISO New England, who is not in this chart, who are adding unserved energy, so magnitude of the shortfalls. And with the exception, and the only exception here in the US is the LOLP that's used by WEC, the Western Electricity Coordinating Council, which had a 0.02% LOLP criterion back in the day. In contrast, most of Europe was operating with loss of load hours. And actually, different countries in Europe had different preferences for their reliability between 3 and 8 hours per year. Now, I will say, before we continue, that these metrics doesn't mean that you're going to have even an expectation 3, 4, 8 hours of outages per year. It means that in those 3, 4, 8 hours, you might expect to have to operate some contingency plans or some contingency resources to avoid losing load. And there are some of them that we're going to explore later. Finally, in this list, you can see that Australia, at least by 2020, had already moved to our normalized unserved energy metric. They were aiming for what would be something like 2 parts per million of energy not served. And that was the metric they were using. As I mentioned at that example from ERCOT, from that curve that we were seeing, one of the things that was in that curve at the bottom was the planning reserve margin. And now we're going to explain what it means. The planning reserve margin is a key calculation that comes out of resource adequacy assessments. It's a single value that tells us what is the buffer, the capacity buffer that we need to achieve a prescribed level of reliability such that we can have enough resources to either by redundancy or by overlapping of diversity in their production, achieve enough generation to meet load with the prescribed levels that we're trying to achieve. You can think then that a lower loss of load probability will require a higher PRM, just like that chart from ERCOT said. As you move to the right in that chart and you had a higher planning reserve margin, well, that needed higher levels of investment, and that generally leads to lower levels of loss of load probability. The planning reserve margin shows up in all across the country, even regardless of the jurisdictional or industrial organization. In wholesale markets, the planning reserve margin is part of the capacity obligation for load-serving entities. So once the ISO establishes a planning reserve margin, it looks at each load-serving entity, each firm that is purchasing power in the wholesale market to serve its customers, and tells it, okay, you got to show me that you're purchasing enough capacity to cover your load, your peak load, plus this extra buffer. And that way, we're ensuring that you are making sure that you have enough reliability for your customers, and you're not, free riding on the rest of the market. In the case of integrated resource plans, which is what happens largely in the West and portions of the Southeast, the utilities, vertically integrated utilities, are planning systems that have an excess, this planning reserve margin, and they have to determine what is the right excess to build such that the system meets or mildly exceeds the reliability performance, but it doesn't over exceed it and make the system super adequate, because that, of course, has consequences for ratepayers who have to foot the bill for these larger investments for levels of reliability that we might not be socially agreeing on. And so the way these planners do it is that they calculate the planning reserve margin, and they build this into their optimization models and say, all right, my optimization model, we're going to meet this load, and then we're going to meet this additional buffer. And so this is what we have to build, and so forth. Another useful concept that comes out of the resource adequacy process is the capacity gradation. If you remember from that MISO process, there were two key outputs of the whole resource adequacy assessment. Well, one's the planning reserve margin. The other one is this capacity gradation. The capacity gradation tells us how an individual resource contributes to resource adequacy. I'm going to quickly anticipate, you might see it here down below, the ELCC that some of you may have heard, the effective load carrying capability, is a classic method to calculate this. It's not the only method, but it's a typical method, and I'm actually going to use it to explain how you calculate this capacity credit. The capacity credit is very importantly used in wholesale market settings, because you want to allocate. There are all customers are paying for capacity. There is a wholesale market or some sort of bilateral market set up that such as customers pay for capacity for a certain reliability level. But then you have to turn into the producers and allocate those payments. So, okay, who gets this capacity money? And so the idea is that you get the capacity money based on how much you contribute to resource adequacy. And that's what the capacity credit allows you to do. It also helps you to determine whether load-serving entities have fulfilled the procurement requirements. In IRP, integrated resource plans that don't have wholesale markets, you can use resource adequacy, and you can use, capacity gradation methods to connect the capacity expansion model with the resource adequacy constraints, such that you can pass information about what resources are contributing to adequacy more than others, and then let the optimization model use that as a constraint to add resources in least cost ways, such that they can meet not only energy targets, but also these adequacy constraints. As I mentioned, I'm going to explain in particular the ELCC approach right now, since it's such a widely used approach for capacity gradation, both in ISOs and IRPs. So the ELCC method, the effective load carrying capability approach, uses the LOLE study, this probabilistic risk assessment study that we already described. You remember those probabilistic curves for load and generation. That sort of study is used to run an experiment, and the experiment answers the question: how much does reliability improve when a resource is added to a system and compared to that of perfect capacity? So the idea is not only to test how more reliable my system might be when I add a certain resource, but I want to measure that in a way that is comparable to other resources. And that's what we use this concept of perfect capacity. So you can see here in the chart to the right that we starting in number one. We have a base case. In this particular case, this is showing how it works with renewables, but it can work with any type of resource. We're starting in the best case, and you add a resource of any type, a certain amount of resource. Typically, you establish 100 megawatts, maybe 500 megawatts. You add a certain amount of resource, and you move to number two. And if you see here, the chart, the axis in the left is showing the loss of load expectation. As you go down, you get a more reliable system. In general, anytime you add a resource to a system, you will make the system a little bit more reliable. It's very rare that I will add a resource to a system that does absolutely nothing for reliability. That will be a really poor resource to add. So in general, you add a resource. Now, depending on the resource, that dot in number two might go even further down or further up. That's part of what we're trying to gauge here. So imagine that you add this resource and you rerun your simulations, and now your LOLE goes down to, let's say, 0.06. Now you know how much your system is able to, how much your reliability improves. And then you start removing, in this case, perfect capacity. You start removing essentially, how to explain it? The idea of perfect capacity is a theoretical concept that describes a resource that is perfectly available. Each time I add 1 megawatt of that resource to the system, I get 1 megawatt of resource adequacy, and hence this is the most my LOLE can improve, or LOLP, or whatever metric you want. The most it can improve as I add a resource is that benchmark. And so what this is doing is essentially saying, now, if I added this amount of resource, of renewable resource, and I got this benefit, and then this is equivalent to adding this amount of smaller perfect capacity and adding the same benefit. The ratio of these two capacities is what we call the capacity credit of this resource. In this case, a renewable resource in this example. Typical values for, this is an example of some accreditation values from PJM, and this is particularly showing a change in their accreditation approach from the 2024-2025 year to the current period. You can see how drastically things change. We're not going to discuss why that happened, but this is shifting from different types of ELCC approaches, and it kind of suggests how important it is to get these assessments right, because things can change quite dramatically depending on how you do your resource adequacy assessments. And these have very direct important implications on both payments for these types of resources, these technologies, for capacity, but also to ensure that the system remains reliable. You can see here that typically onshore wind has a 35%, in this particular case, 30 to 35% of capacity credit. Solar panels have 9%, 10%. In particular, solar panel, as you can think, as you add more solar panels to a system, all of which have the exact same production profile, it is well known that the contribution of each additional solar panel to adequacy is lower and lower, because we're not adding diversity to the system. We're always meeting load at the exact same time. As you can see to the right, most thermal and nuclear resources have much higher capacity ratings because they're able to either be serving load consistently, they're flat generating, or they can be adaptive to load needs such that they can be present in the most required times. A classic example of that is a diesel engine, which is so expensive to operate that is only used in specific hours of the year, but it's called and easily made available on the most stressful hours, and so its ability to contribute to adequacy is always relatively high. Now, to achieve resource adequacy, here we're going to talk about the ways in which we can construct either regulations or markets to achieve the objectives that our resource adequacy assessment is proposing. In vertically integrated states, the typical approach is using, as I mentioned, integrated resource planning. It's a process that ensures that we're meeting projected load with the least cost, accounting for projections of load, fuel costs, technology declining costs, etc. And it has an integral component devoted to resource adequacy, try to ensure that the least cost system that is being built is also adequate and meeting, minimum levels of reliability. In restructured states, which are the ones that are shown here to the right, we have three different approaches. We have capacity markets, which are specific markets where the system operator requires firms to go and make a bid to supply demand, to supply a certain amount of capacity to achieve the planning reserve margin that the ISO has designed. And this market operates on the side of the energy market, and it usually looks forward anywhere between 6 months to 3 years and says, all right, in 3 years, I'm going to need this amount of capacity. Who's gonna fulfill it and what price? And then different resources put their bids and they construct a supply curve. They intersect that with a demand curve, and there is a capacity price that comes up that everyone gets, and that's a strong signal for investment in these markets. There are some hybrid approaches in KAISO, like the ones in KAISO, MISO, and SPP. For example, in MISO, they run what's called a residual capacity market. They let utilities figure it out with generation owners and transmission owners who's going to get what capacity. And when there is some gaps remaining, those go to a residual bidding or auction process where they can fill in the gaps. And then there are energy-only markets, which is ERCOT, where capacity doesn't have a price. We're going to cover this a little bit later in this presentation, but it is an approach where just the regular bidding in the day ahead and real-time markets produce cost signals that should be enough to warrant or to induce investments for adequacy in the long term. So I'm going to cover briefly these three different approaches to ensure adequacy. This is roughly we're moving from we're getting to this space when we're talking about adequacy and investment, and in part because investment in power system has, of course, many implications. One of the big ones is making sure the system is reliable. What you're seeing here to the right is a nice framework for all the models that are typically used in integrated resource planning out of our recent work in best practices in IRP. And you can see to the right, we have a resource adequacy assessment model that is talking to this capacity expansion model in different ways. The way it's talking right now is that it is producing capacity accreditation values that are fed into the capacity expansion model to ensure that the capacity expansion model, when choosing, say, to put an amount of solar, is not only accounting for the affordability of that solar resource on the energy, but it's also accounting for the fact that it might not be available in the right times to meet capacity. And so it has to achieve that trade-off. This arrow that is connecting them both directly is an aspirational model where adequacy and capacity expansion models can work linked directly in a single model, essentially a stochastic or probabilistic capacity expansion model that doesn't quite exist yet. But there are some emerging efforts that can go in that direction. So on the restructured states, the ones that have capacity markets, I'm going to explain a little bit how these capacity markets work and what they are. Capacity markets and payments are mechanisms that provide revenue for a resource in a market setting to contributing to resource adequacy. One important thing is between markets and payments, there's a distinction here. Markets are competitive. So you obtain out of resources that bid into certain types of auctions, there is a capacity price that is established, typically once per year, sometimes once per season, and most of the time across different zones, recognizing that some of these ISOs cover large territories, and so they have different transmission constraints that make their adequacy assessments non-trivial. But the markets are essentially producing a capacity price. In some cases, the payments and the establishing of this quote-unquote price is done administratively, and it's just set at a certain fixed value, typically using what's called the cost of new entry, or CONE. The CONE is really the annual payment that you need to cover a typical gas turbine that is used as a reference for what building capacity quickly would be. These gas turbines are typically operated very little in the year, 1 to 2% of the hours, because they are really capacity resources. They're there not to operate continuously because they're fairly inefficient. I'm making the decision here between gas turbines and combined cycles, which are fairly efficient. These turbines and diesel engines are largely used just to show up in those peak hours, just to serve demand when the times are more stressed. Generally, ISOs have used the cost of deploying some of the resources as a reference. And in some markets, not in the US, but in some markets, that's the payment that some capacity resources can get. Just directly, you get the payment of the equivalent of this cost of new entry. In both cases, these prices of payments are paid by load-serving entities that are, withdrawing power from the system, from the wholesale system, and then serving it to customers. So they have to pass this cost to customers via retail rates. But in the case of regulated entities, this capacity payment might include a return over investment, of course, that is part of the regulatory compact. So the designs and targets for these capacity markets are, of course, dependent on resource adequacy assessments. And there is a whole lot that we could discuss here that we don't have time for. But I'm going to show just very briefly some of these elements and how they work. So capacity markets has multiple design features, but at the core, they are set up as forward-looking auctions. So every year, and sometimes every half a year, but mostly every year, the ISO goes out and says, okay, we need this amount of capacity for the next few seasons, and then it opens this for bidding. And different types of resources have to bid and say what kind of cost they're willing to, or what kind of price they're willing to receive to produce capacity. And those resources have to be thinking and knowing that they have a certain capacity credit that they have to take into account. That's why if I'm bidding as a solar resource that I know I won't have power in the middle of the night, I have to be careful not to bid too low or bid too high, or even to participate depending on how the market is set up. So there is a whole lot that goes in here into how to define my bids and how to participate. But you can see that the capacity market is set up by compiling all the bids in a supply curve that is here in this figure in red, and then creating what's called reliability-based demand curves, which are curves that are artificially made, administratively made. It's not that demand is showing up and saying, this is what I'm willing to pay for reliability. This is the ISO taking a best guess of how much they're willing to pay to achieve certain reliability targets, and then going all the way up to the maximum value that they're willing to pay which is the value of lost load, which is when I have too little quantity. And of course, you don't want the market to settle at that level. That's a really poor signal. You want the market to clear, as it says there, clearing price at those lower target levels, where I'm achieving the reliability targets that I want at prices that are reasonable. Finally, just to cover the final option here on how you can procure adequacy, how you achieve adequacy. ERCOTs, some markets in Europe and elsewhere operate with what's called an energy-only approach. So they don't have capacity markets. There's only an energy market that is designed to have the energy price go really high in certain times of year. Some of you might remember from Winter Storm Uri in Texas, there were all these issues where the energy price in Texas during those times went up to the ceiling, which I think at that time was $9,000 per megawatt hour, which is very high. And that was a consequence of a market really being absolutely out of power and reaching that ceiling as mostly a signal that more investment was needed. Unfortunately, as I mentioned, that price is funneled down to customers. So there were many customers, the few ones that had electricity, had to pay exorbitant costs, and there were some interventions that had to be done for that, and revisions that came to their energy-only market to prevent this from happening again. So the key element here that in general in operating these curves, how the energy market reaches that really high price is that there is a demand curve that is operating. It's similar to the one that we just saw, but essentially it's a demand curve that you can think as the reserves in the market starts getting smaller and smaller, and that means that my system operating tighter and tighter, the price starts going up directly, not as a consequence of what machine is operating, which is typically the marginal machine is trying to give an extra amount of money, what's called scarcity pricing, to create these incentives for investment later on. We're going to cover these ORDCs, these operational reserve demand curves, later in the economic perspective. You can see here how there is this connection between technical and economic happening as we need to ensure adequacy, and we need to bring in these economic aspects of how we ensure adequacy at a least cost for customers. Now we're going to go back to our three core elements in bulk power system reliability, and we're going to cover kind of briefly operational and contingency elements. So in operational reliability, we're really talking about the ability of the power system to balance supply and demand in real time. And that means managing ramping constraints, variability of load that's happening all in in the minutes to seconds. And the way it typically happens here is with different grid services that could be operated through markets or just provided by different firms, different generators, with or without any compensation. Some of them you may have heard. Frequency control is one of these. Voltage control are classic grid services, and these are usually defined in different types of hours. I'm going to refer to a few of the more common ones. For example, frequency and voltage control are used to maintain the stability and security of the transmission system. And they typically operate, voltage control operates in the very low, seconds to minutes range. And frequency regulation operates into the, few minutes. And that means that there are machines that are looking at certain variables in the system. They're tracking the frequency and the voltage, and they have internal devices that are adjusting little by little their output to provide either a higher or lower speed in the rotating machines, or more or less active or reactive power, both which affect voltage and frequency. So these services are typically provided by what's called operating reserves, which has these machines that are not only doing energy services, but they're only using some of their output to regulate, and they're typically compensated for that. On the contingency side of things, the contingency operation consists on actions that are employed to prevent further system degradation or to halt a degradation process when you're in an emergency state. In this case, typically contingency operations are mostly entirely technical. The cost of how you operate and on how you achieve, especially when you avert some of these crises, it's typically secondary, in part because this happens very little, and in part because a blackout is a substantially much higher cost on face value than any of the types of costs that you can incur to prevent or to restore the system during after a contingency. Contingency operations include the draft of contingency plans, or it's sometimes called defense plans, which is a mix. It's usually a manual, but it's a mix of strategies. Some of them are automatic, programming different components of the system. Some of them are manual. A classic one is this rotational load shedding events. These have been also on the news at times. These prevented, typically these are the ones that system operators use as a last resort to prevent a full blackout when they start shedding load, specifically in places that don't have enough generation to serve, and they just have to shed the load, balance the system, and then slowly, as more power becomes available, they can bring the load back and do that carefully such that they don't induce strong dynamics reactions in the system. And the other piece that is taken care of here is the restoration actions that re-energize the backbone of transmission. And this is called the black start, which is a specific type of service that, unfortunately, as someone mentioned, is used in Puerto Rico more than they would like, but is rarely used in reality. And it's actually always a kind of a question. How is it that the system is exposed to black start operations maybe once every 10 to 20 years? It's really rarely used. So contingency operation relies on different types of reserves that are operating in different timeframes, typically longer timeframes. There are spinning reserves that are these reserves that I was mentioning are used also for frequency and voltage regulation. There are operating machines that are reserving portions for the production, not for the market, but for these what's called ancillary services. There are certain types of machines that are non-spinning, and this spinning and non-spinning, of course, is a legacy of the times where we had, rotating machines fitting our grid. As these terms are going to become somehow potentially might not become as useful as we think about many supply side resources and demand side resources that are not spinning at all. But the idea is that the non-spinning reserve are machines that are offline. They have to be brought online and then synchronized to be able to support. And then there's black start units, which are the specific generators that are equipped with specific equipment that are able to start the system from a blackout. Let's turn now to distribution systems. As I mentioned, we spent a fair amount of time talking about the bulk power system. That's going to be the bulk, pun intended, of our presentation today because it's kind of a hot topic. It's where a lot of the reliability discussions is happening. But I didn't want to not talk about the distribution system and what it implies. So reliability in the distribution system is generally seen as the ability to deliver uninterrupted services to customers. And it's important to know that around 90% of the interruptions that you might get in your home or in commerces, the ones that happen at the customer level, are actually originating in the distribution system. Is that tree branch that fell on top of an overhead line during a storm? Is that squirrel that got fried by trying to chew in the wrong cable and produce a short circuit? So those are the kinds of things that are more localized, happening on a much more frequent basis, and it's not quite the types of larger events that we were just examining in the power system in the previous portion of the presentation. If I have done a good job at using these two terms, it means that you rarely heard me use the word interruptions that I was talking in the bulk power system. I should have been using the word outage, and I hope I did. An outage is when an asset cannot perform its normal functions. So what the bulk power system, resource adequacy process, and operational reliability are doing is preventing outages, preventing assets from going out of service. And interruptions refers to the availability of electricity to end users or customers. And so that means that an outage could cause an interruption, but not always. For example, if I have two parallel lines that are serving one customer and they're sized such that they can each one of them individually serve this customer, if I lose a line, if I have an outage in this line, I can still serve my customer. My customers does not have an interruption. Let's say an example of the N-1 criterion, which is a criterion that is used to ensure that the system is reliable. And it's typically used in transmission systems to ensure that portions of the transmission system can take on load of other portions that might fail, but continue without producing an interruption to customers. And at the same time, interruptions can be caused by things that are not outages. For example, a plant maintenance. If a utility has to replace a pole, it might have to interrupt you for a couple hours, and that's not really an outage, or it could be called a plant outage. But this is to say there should be a distinction, and I make the distinction here because the bulk power system is largely focused on outages, and the distribution system is largely focused on interruptions. From the metrics perspective, the metrics in the distribution system, there has been several decades of experience on tracking the performance of distribution systems through understanding the interruptions that occur to customers. These are codified in the standard IEEE 1366, of which its most current version is 2022. But this standard was, I think, originated in 1990 something, 1998, I think was the first version, or even earlier than that. These metrics, as opposed to the resource adequacy metrics that are the outcome of simulations, these metrics actually summarize what has happened in terms of interruptions in actual circuits, feeders, or entire utility systems, but they're focused on actual events. And many states do impose some maximum or minimum standards. As in the resource adequacy world, we have metrics and we're trying to invest the system to achieve a certain level. On the distribution system side of things, the utilities are incentivized or required to achieve at least minimum standards, typically at a circuit level. But in some states, the utility has to file a reliability performance report. And typically, they're required to describe if there are specific customers or circuits that are underperforming, that are producing a very low reliability experience for customers, and propose targeted interventions to improve those. So there are certain basic metrics in the standard, the IEEE standard, and these are some that you may have heard. SAIFI, SAIDI, CAIDI are typical ones. I'm not going to go in detail what these are, but I wanted to, because you can see this, you can read this later with more time, but I want to convey that these are doing the same thing that some of these resource adequacy metrics were doing. SAIFI is tracking frequency, the average frequency of interruptions. SAIDI is tracking the average duration of interruptions. The CAIDI is tracking the duration of interruption for customers that are interrupted. So if you're a customer that gets an interruption, I take all the customers that were interrupted and I get the average of their duration, as opposed to the system level where I just take all my population and determine what is the average frequency and duration for those. Another important, not exactly metric, but concept is the MED, the major event day, at the bottom of this table. And the major event day is a distinction that was established a while ago, where with certain statistically defined thresholds, a utility can classify one day as a major event day, and then it might get to not count that day towards the calculation of SAIFI and SAIDI, or it is required to separately report the SAIFI and SAIDI with MEDs and without MEDs. The reason for this is that major event days do vary substantially across time, and particularly because weather varies across the years. And so even though there might be trends of how weather is behaving, I could have a very dry year and a very wet year, and that might have very different implications for how load was showing up and how my system was performing. And so they try to keep track of the performance without the major event days to get these long-term trends, and then track some, in many cases, are more pressure to also perform under major event days. In one of the latest revisions of the IEEE standard, they added a number of customer-centric metrics. And the idea was that these original metrics were all focused at the very system-wide, sometimes feeder level, but they were not really tracking what happens with customers. And so they added some of these metrics that are, the SEMI, SEM, and some others that are listed here. All of these are generally counting number of customers that are going through certain types of outages or interruptions, either momentary interruptions, multiple interruptions. There's different flavors. They still remain, in my mind, a little bit incomplete in that they're not really establishing a standard for a specific customer. It's just saying, hey, you have a certain amount of customers that are not having a good time. It doesn't quite lead to the specific action to say, oh, customer A needs some help because their particular standard for reliability is not good. But there are, evolving progress to go in this direction, in particular with smart metering or AMI that allows customer-specific reliability metrics to be developed very easily. The way the distribution system or distribution utilities track interruptions is using what's called an outage management system, or OMS. And this is software that's used by utilities to manage the power outages, to detect them, to ingest them, to locate them in their GIS systems, send the crews, and then restore power. They were originally developed by some utilities in the late 1970s, but then in the late 1980s, some of the first commercial outage management systems were developed. And here in this graphic by Litton Software, you can see how the outage management system is really integrating pieces of data from across the utility, mostly the distribution system level, and integrating smart metering data, call center calls, and then identifying in the GIS, in the map, where the event may have happened, given how the calls in the past, this is how they were. They detect the outages by just someone calling and say, I don't have power. And then someone else calls, I don't have power. And you put those on the map and you start seeing how that correlates with certain portions of your grid. And you have a better idea as a crew on where to look for something bad happening, either a tree falling or a transformer exploded. As smart grids and smart meters have been introduced into the system, now we have automated ways to find where the interruptions may be coming, and that allows crews to go much faster to go and restore power. These outage management systems are tracking each one of these interruptions and storing them, and these are used for further information and to establish the safety, and other metrics. You can see here I extracted some of the utility outage maps are feeding directly from the OMS. This is the source. This is a particular map from PG&E where it's showing customers affected in different parts of their service territory. And there are now is this very common for many utilities, especially large ones, who have these maps available to customers. As we talk about in resource adequacy, how to achieve distribution system reliability, or sorry, how to achieve adequacy, this is kind of the equivalent one slide on how we achieve distribution system reliability. And ultimately, it boils down to both how we operate the system in such a way that it can be more reliable, and how we build the system to make it more reliable and potentially more resilient. Distribution system planning is one of those processes. Here to the right, you're seeing an integrated distribution system planning process that has right there in the middle a reliability and resilience need block that is feeding, among other blocks, into a grid needs assessment that then goes through a regulatory process to allow for certain approvals of projects and potentially investments that maintain reliability in the grid. And there's a whole lot that we can talk about the types of models and data that are used, but there was too much for today. There are internal utility planning processes where the utilities are conscious about the reliability issues in their systems. They know about circuits that underperform, and they keep developing plans to either underground some overhead systems to make them more reliable, sometimes to add redundancy to ensure that customers can remain with power, etc. And as I mentioned, there are some regulatory requirements for reliability reports that are also another way in which at least regulators can look at certain underperforming areas and suggest for investments. Now we're going to be on the tail of our presentation, and we're going to go out of the technical side where we reviewed bulk power system and distribution system aspects of reliability, and we're going to look at the economic perspective, or what I'll call the cost of unreliability. Now, power interruptions cost money, and it's actually surprisingly hard to find power outage specific costs. Usually when you have the cost of big events, you have costs that include a lot of the infrastructure laws, insurances, and things that are not specifically power related. But this is an effort made by the Department of Energy this actually is the Executive Office of the President from 2013, trying to put a value on power or energy not served. And there are multiple ways in which people and businesses are affected by the lack of power. It can be the loss of food that was refrigerated, wages that you couldn't get because you couldn't get to work, losses on production in case of firms that have manufacturing, the cost of running a generator if you're trying to avert that interruption by trying to mitigate it, the cost of relocating if there's no power for too long and you need to relocate out of the area. So all the different costs are playing a big role. And there are recent estimates from 2015 that puts average annual losses as high as $150 billion. So there's a fair amount of money here in terms of what costs to not have power. This is a framework that we developed a couple of years ago that shows different pieces on how to go from the threat of a hazard or a hazard all the way to deciding what kinds of mitigation strategies should I deploy that are cost effective, such that they compensate the amount of money that I'm losing because I don't have power. You can see that a lot of the words that we already described on the technical side were covered in the left-hand side of this diagram. Interruptions, the magnitude, duration, and frequency and timing, all of these affect eventually a certain amount of energy not served. And then I can have a certain, that energy not served has a cost using a concept called the value of lost load that we're going to cover now. So the value of lost load is a key economic concept tied to power system reliability. And relying here on the definition by my colleague, Will Gorman, the value of lost load is an electric industry metric meant to encapsulate the societal benefits of reduced outages in a monetary figure. The value of lost load is essentially the cost of not having power. And as you can think, it varies substantially by customer, it varies by location, it varies by time of year. At the core, the idea of the value of lost load, this is a similar chart for what I showed from the ERCOT chart at the very beginning. This is showing here that the value of lost load is the curve that goes from the right all the way up. As I have less reserve and I have higher likelihood of losing power, my value of lost load, my total value of lost load, the amount of money that I'm losing as a society for not having power shoots up. At the same time, I have a linear cost for capacity costs. As I want, a more reliable system that has a higher reserve margin, I have to spend more. And that produces this total cost curve that is a convex curve. It's a curve that has a certain minimum point. We saw this also in the ERCOT chart. And that means that there is a balance between the value of lost load cost and the capacity cost. There is theoretically a point where I can produce this. But now the question becomes, where does the value of lost load come from? How can I produce the curve that's showing here? Or in general, how can I produce value of lost load? My group in LBNL does a fair amount of work trying to measure the value of lost load. And we have derived multiple different methods. We're coalescing into something that is what's called a hybrid method, where we're mixing surveys with models. Very briefly, there are a few different ways. Traditionally, survey-based methods, what's called stated preferences, is the way that it has been used to measure the value of lost load. Typically, you go to customers and you ask them, how much are you willing to pay to avoid an interruption of this sort, or to not have power at this time of year? And they tell you a number, $100, $150. And we translate that into a normalized monetary value. There is all the way down here a reveal preference, which is a method where we see how people make day-to-day decisions in different purchases or that typically relate to mitigating the impacts of interruptions, and that reveals how much they're willing to pay to avoid those. The methods that we're using right now, the cutting-edge methods, are regional economic models where we can track the relationship between having or not having power and the production across many types of different economic sectors. And we can measure in GDP loss the impact of not having power, and we use the surveys to calibrate these methods. And this is the hybrid valuation method that is kind of the cutting edge in measuring the value of loss load. There are largely two ways to apply the value of loss load. What I was showing in the ERCOT example and the previous curve is at least cost. We're looking at that minimum cost where we had just the right amount of capacity and just the right small amount of value of loss load that minimizes the total cost of the system. Another approach that's commonly used is a cost-benefit analysis, where instead of trying to find the mix of investments that minimize cost, I'm trying to say what is I should get as many of these types of mitigation strategies as possible, such that the cost benefit of those strategies remains above one, meaning that the cost of these strategies is lower than the benefit that are derived when the benefits are calculated by using the value of loss load multiplied by the amount of energy that I won't get, and I get a certain energy not served. And if the benefit that I'm getting for mitigating that is above the cost, I should invest in that. A couple of tools that we have for applications of this is the ICE calculator, which is the tool that is geared towards, is based heavily on surveys that have been developed across the country, and is used to calculate the customer cost of short duration localized interruptions. And then we have the POET, the Power Outages Economic Tool, that implements this regional economic model approach that allows us to understand the costs of long duration, larger, more widespread types of interruptions. And these can be used in complementary to calculate the costs of or the different strategy to mitigate interruptions across the entire power system. One aspect that I said I was going to cover here, as we are talking about the economics, is the creation of these operational demand curves. And this is where value of loss load is used directly to construct this curve. You can see that in this curve, what's happening here is that as I go to the left and I get less reserves than I need, the price of those start going up as I want to give a signal to investors that I do need more reserves. If I have too many reserves to the right, the price is very depressed, it's very low. That means that I'm all right. I don't need more reserves, so don't give me more. Of course, markets try to clear at some point here in the middle, but the value of loss load is used here to give the ceiling, because the idea is that as I reduce my reserves and I get to a point where I'm going to have the value that I'm willing to pay is the value of not having power, and that's the value of loss load. Calculating this value, of course, it's a whole challenge. I'm going to briefly cover some of the industry applications for the value of loss load. As you just saw, the operational reserve demand curves require the value of loss load. It's typically also used as the price for capacity or for energy during certain types of emergency events. In ERCOT, the value of loss load is also used to create either system-wide, what's called system-wide offer caps, which are ceilings for their energy markets. But this was discontinued, especially after Winter Storm Uri, as I was explaining earlier. It has been used to determine this economically optimal reserve margin in that one of the first graphics that I showed. In other ISOs, the value of load is typically also used to assess in a cost-benefit analysis like CAISO. They are willing to put more transmission as long as the avoided expected energy monetized by the value of load is above the cost of that transmission. In distribution system levels, you can use the value of load for avoided energy supply costs. This is, for example, in New England, they do this approach where they establish a value of load and then is used for any type of utility investment that is geared towards mitigating potential interruptions. And in this case, they came up with a $26 per kilowatt hour value of load in 2018, and then the 2021 study almost tripled that value. That tells you a little bit of the complexities of calculating the value of loss load. Ultimately, we could get to a point where we can use the value of loss load and the concept of reliability within the planning process, such that we internalize reliability as part of the objective functions that we're trying to, or as part of the cost that we're trying to minimize in an objective function as a society. This approach has not quite resulted yet, even though this technique was proposed in 1990s. There is a lot of resistance to incorporate the value of loss load into the actual costs that are calculated in any type of investment approach, investment decision making by utilities, in part because it's so hard to calculate. Um, so what happens in reality is that in bulk power systems, most of the IRPs are using constraints, are using metrics. So we are not really building to achieve the system that minimizes the value of lost load or that makes the value of lost load part of the overall cost. We're choosing this 1 in 10 or zero point 0.1 days per year constraint, and we're willing to pay for that level without really understanding exactly what is the value of lost load implied there. And there are all sorts of assessments that have been done to point in either direction. Either the system is actually covering a value of lost load that is way higher than what customers should be paying, and others say the opposite, that the value of lost load is way lower than it. And that's because it's hard to measure. In restructured state, as I mentioned, the value of lost load is used to inform the ceiling of auctions. So there is some use, but it's not really used more detailed way to inform the shape of these curves. And resource adequacy assessments and the planning reserve margin auctions, all of those remain entirely technical. And we're not, building systems again to minimize or to achieve a certain value of lost load level. Distribution systems is more or less the same. Um, Utilities can consider the value of lost load to justify certain types of investments, and they do, but it's not as common as you would think, in part because it requires measuring the value of lost load for that particular circuit, which is very time consuming. So this leads to kind of the last little bit here in the economics is, well, why don't we use the value of lost load more extensively? And that's in part because calculating defensible estimates of value of lost load is very expensive. Um, the recent project that we run to calculate values of lost load for dozens of utilities across the country was a very expensive effort that might not be undertaken by a single utility. And it was actually the result of a joint effort. The surveys have drawbacks. They're the easiest way to calculate the value of load, but this might be speculation or bias. And then on the flip side, the regional economic models that we have used are typically not grounded, and that's why we have tried to use the surveys to calibrate the regional economic models. Even then, when you do calculate the value of lost load, there are just multiple ways to measure it. You can calculate the cost of not having power, of just having one interruption, the cost of having an interruption for a certain length, and then depending on the length of the interruption, the cost changes non-linearly. So it can be $1 per kilowatt hour not served. It can be $1 per kilowatt. It can be $1 per hour of interrupted. And all of these can lead to different results with different consequences. So still, lots of the work to do to bring in this core element of economics and reliability into practice. So now as I'm finalizing, I'm just going to leave you with a few key takeaways. Um, Hopefully you have understood that electric system reliability is about having enough supply, demand, transmission, and distribution resources to keep electric service up almost all the time. We cannot achieve, and hopefully will not achieve, perfect reliability because it will be extremely expensive. Even if you had a big battery pack in your house and a big solar system, we have already calculated that that's going to get you through most, but not all of the possible long duration interruptions that you could have, especially if you want to operate all of your end uses. Bulk power system reliability focuses on having enough generation to meet load, which is resource adequacy, enough resources to keep the system operational stable, which is operational reliability, and have plans for strategies for emergencies, which is contingency operations. So 3 buckets for bulk power system reliability. Resource adequacy is tightly linked to investment decision making, and in wholesale markets, the way we set up the markets is intimately connected to both the need to send economic signals, but also to achieve certain resource adequacy objectives. In the distribution system, reliability focuses mostly on tracking these more frequent and shorter interruptions to customers. As I mentioned, 90% of interruptions that a customer will suffer will come from the local distribution system. And so the key here is to track these interruptions to understand where things are happening and for the utility to take targeted action to ensure that customers receive a better quality of service. And perhaps the aspiration here is to start moving towards a point where we can ensure that each customer in a distribution system service territory has a minimum level of reliability. And then finally, as I was describing, the value of lost load is the monetary link between reliability and system performance, but the calculation is challenging, and its adoption, as widespread adoption, has remained also challenging. So thanks so much. I have here one question on the chat, and I think -1 minute to take it. So Miles, up to you if we have a couple more minutes to at least answer this question from Ian.
Yeah, let's address the question, and I think if and I don't see any others in the chat, so I want to address this one before we drop.
All right, the question is really well framed, so I'm gonna just read it and answer it right away. The question is, how does all this what I've talked about reliability interact with rapid demand load growth? If load cannot connect because there's no available capacity, can the value of this load be used to estimate that impact? So there's a lot packed here that's really interesting. Um, First, demand growth is something that you would want to assess as a scenario in your resource adequacy assessment. Turns out that the load levels that go in resource adequacy assessments are trying to capture mostly weather variability and some economic performance variability, but rarely the ISOs put different load growth levels and look too much into the future to assess how wrong their calculations can be. So there is already a limitation there in how we're assessing, at least from the resource adequacy perspective, the likelihood of the system to have shortfalls because load is growing faster than anticipated. Um, the value of lost load might, so I think what's implied here is that if load cannot connect, of course, for people, this large load, especially data centers, they're not allowed, they're not like plugging, it's not like they show up and plug something in the wall and they get going. We're talking about load levels that are the size of a city. And so they require substantial permitting and coordination with the system operator to actually connect and start drawing power. And so if load cannot connect, um, I don't know if the value of lost load might be the right exact way because this is power that was never produced. But certainly you could try to assess the economic impacts of not having that load operating, which is, I think, what some people are trying to do, is if this load doesn't show up, then what is the economic impact of that and who suffers the impact? Similarly, if that load shows up, what is the economic benefit of that particular big load, say a data center, if it's a punctual load, or if it's smaller loads, what are the economic benefits of that? So I don't know, Ian, if you want to add to the question, if I did interpret it correctly, you feel free to. Okay, you said that is helpful. Awesome. So, but yeah, this is something that is being tormenting resource adequacy planners, how to deal with these load levels, and there are multiple strategies that are pretty outside of the assessment itself that are being taken. One of the key consequences that you might think is that if these load levels if we were to build the grid to meet these load levels and they don't show up, we'd be stranded with a chunk of assets and infrastructure that we might not need for decades. And that will, customers will take the toll of that. So that's the pressure that regulators in particular and market operators have in terms of how to meet these load levels, but being prudent about it.
Thank you, JP, and thanks Ian for that question. Thanks to everyone who joined us today for the informational webinar. As I mentioned, the recording will be available on the webinar website, and we'll look forward to seeing you all at the next one in July. Thanks again, JP, and see everyone soon.
Yeah, of course. Thanks, everyone. There's my contact here, so feel free to reach out if you have any further questions.